This screencast is one in a series on process calculations, and the title is Some Important Types of Single Units. The content is the separation unit, the mixer, the splitter, and some ways to combine single units into bypass or recirculation. The separation process has the following properties. It's typically a physical process which involves no chemical reactions. It has one input stream with at least two components, the components that should be separated. It has two or more output streams. And what is an important characteristic is that the concentrations in the output streams differ. For example, the mass fraction of A in stream 2, one of the outputs, is different from the mass fraction of A in stream 3, the other output. In terms of equations, we can set up one mass balance equation for each element or component, whichever we use, for the separation unit. And they could look like this. The first one is the mass balance for A, which says that the flux of A in stream 1 equals the flux of A in stream 2 plus the flux of A in stream 3. And we have the corresponding equation for the component B. A mixer is simply a unit where things are mixed. The properties are the following. It's a physical process with no chemical reactions. It has at least two input streams, which should be mixed, and it has one output stream. But the most important thing here is that the concentrations in the output streams differ from the input concentrations, so that the mass fraction of A in stream 1 differs from the mass fraction of A in stream 2, which also differs from the mass fraction of A in the output stream, the stream number 3. The equations that we can set up are in principle the same ones as we could set up for the separation unit. It's one mass balance for each element or component. And in this case, the equations become, starting with A, that W1A plus W2A equals W3A. And we have the corresponding equation for component B. The splitter is somewhat more complicated. Its properties are the following. It's a physical process with no chemical reactions. It has one input stream with S components. In this case, S equals 2 because we have the two components A and B in the input stream. And it has a certain number of output streams. And in this case, N, the number, equals 2 because we have stream 2 and stream 3 as output streams. And the concentrations in the output streams are identical. And in fact, they're also identical to the concentrations in the input stream. So that the mass fraction of A in stream number 2 equals the mass fraction of A in stream number 3. In terms of equations, we can set up two types of equations for the splitter. One type of equation is the mass balance equation, and we can set up one mass balance for each element component just as we could for the separation as well as for the mixer. However, in addition, we can form what we call splitter constraints, and they indicate and are based on the fact that the output concentrations are identical in all of the output streams. But we can only set up a limited number of independent splitter constraints. And the number is S-1 times N-1. In this case, the mass balance equations are W1A equals W2A plus W3A. And the corresponding equation can be set up for B. And then also, we can set up S-1 times N-1 splitter constraints. And since we have two components and two output streams, we can only set up one independent splitter constraint. For example, the one we have on the bottom, which says that the mass fraction of A in stream 1 equals the mass fraction of A in stream 2. However, any of the following 6 possible splitter constraints may be used. Since we have two components and 3 streams, we can form 6 possible splitter constraints. However, only one of them can be used in our system of equations, because it is possible to show that any combination of 2 of these splitter constraints with the 2 mass balances will form a redundancy. They will not all be independent. The problem with the splitter constraint is that it is non-linear. Therefore, it is necessary and possible to cheat a little bit in order to create a system of linear equations to describe the whole process. If we start with the following 2 equations. The upper one says that we know the concentration of A in stream number 1. And let's just say that it is 0.2. The splitter constraint says that the concentration of A in stream 1 must equal the concentration of A in stream 2. But the second constraint, or the equation, the splitter constraint, is nonlinear. Therefore, we can combine the 0.2 with the right-hand side of the splitter constraint to get that the mass fraction of A in stream 2 equals 0.2. One important combination is the bypass. It has the following structure, and it's composed of various subsystems: the splitter, a reactor unit, and a mixer. And as we see, it has 3 physical streams: 1, 2, 3, 4, and 5. In practice, they are used in various applications, such as when one wants to treat a stream only partially. It's also a way to handle limited capacity of a unit. Another way to combine units is to form a recirculation unit. The structure is the following. It has one subsystem, the mixer. It's composed of a reactor unit, and finally also a splitter. And in this case, we can also identify 5 physical streams: 1, 2, 3, 4, and 5. Now this is used in the chemical industry when one wants to reprocess a reactant, for example when we have a low conversion rate. And it is also a way to maintain high flow rates in a reaction system, which may be necessary from a fluid dynamic or from a heat transfer perspective. The content of this screencast was the separation unit, the mixer, the splitter, including the very important splitter constraint and also the very important way to cheat when you apply the splitter constraint. And it gave us some ideas about how to combine single units into bypass and recirculation.